So what I'm talking about is a part of the publication that Harry's working on about crater like lunar chronology calibration. And I will discuss why crater is specifically important there. So, so for those people who are not familiar with lunar chronology function, it's kind of a tool which we use to find out the model ages of the unsampled planetary surfaces. And so if you see on a y-axis, this is something that is showing the crater density on the surface in logarithmic scale, and on x-axis are isotopic ages. And this is the reason this chronology is based on a lunar and Apollo samples. And here we can see that because we have a very few calibration points for this chronology function. And here we can see that in the younger ages, below 1 billion year, we have a very few points, and Cone Crater is one of them. Lack of the calibration point, right? So lack of the calibration point was also the reason that there was several attempts to create this chronology function was made, and we see there are now several chronology functions, and we want to see which one is the correct one. But we see also the errors that are causing this chronology function, and these errors also include the differences are dependent on what samples ages were taken and how they were interpreted, and what count areas were taken, and different n values. However, we all agree that all chronology functions are suffering from lack of the data points, and that depends on samples. And Carolyn will talk more about it in her talk. And so what Harry was doing was, for Cone Crater, he selected 9 areas around the Cone Crater to measure CSFDs, to measure crater densities on these 9 areas. And he got absolute model ages that were very similar in the range of exposure ages that varies from 16 million year to about 90 million year. On average, he was getting about 39 million year. And this is exactly what the sample ages were telling him. So he wants to narrow down the sample ages. So he considered only the sample ages that were collected around the Cone Crater, which were the station C dash and C prime and C1. And when we see Erickson et al. Ages, exposure ages, these are ranging from about 16 to or 15 to about 30 million years. And these data points, the blue ones, are the absolute model ages that Harry got from his count areas, and the bars are the error bars on these ages. Another thing I want to mention is that he did this when LRO mission was new and there was one NAC data available at that time, and he did all the counts on this area, on this data. Now we have a lot more data than before. We can create DTMs and slope maps, and we can exactly map where the traverse was taken, where the rover goes, sorry, not in this case, but where astronauts walk through. And we also can even see a position of lunar module. So we use a lot of data to create geological maps. And in another publication, which is soon it will get published, we created also overview geological maps of Apollo landing sites, and we also published other landing sites. And in this with these maps, we can see which geological can influence sample collection. And in addition, we also made geological map around the traverses. And here we can see that, as I mentioned, that there were certain stations that were lying on a cone crater ejecta. Not all of the stations you could expect that you collect a material of cone crater. And then, as I say, we have slope maps or DTM data. So we can see a lot more in detail around these traverses. So what I will start doing, I start going to look at the areas that Harry had counted. And then I will just present 3 areas, what he had shown. And then I start looking into obvious problems. Here, for example, in area 9, we see like 2 big craters, which can influence the could add the errors in CSFD measurements. And we see that the variation of the slopes in this region. I would say, okay, I immediately say, no, I won't take this area. Then similarly, we also look into geological map, the extension of the ejecta material of the cone crater. And here we see that not all the areas that Harry mapped are lying on ejecta. And then we also say, okay, these are also the areas that we are not taking in. Here I have to point out that this is dotted material I map. It's also the ejecta material, that like a ray material of the cone crater, and the yellow part is a proximal ejecta. So these are the obvious one that I could say, okay, we don't include them, or we don't consider them. And with that, Harry says that, okay, he will just map the whole area again. But even before that, he mapped the whole area again for CSFD measurements. We can see that these were the points that has the highest errors in there. And that was also causing the sum of all the areas to higher range. So if you compare it with, again, the ages that was previously determined, exposure ages that was determined by Everton et al., and then the recent one from Fury et al., then we see that the sum is kind of closer to the average ages that they are getting. So even though with the preliminary results of Harry, we could see that that this cone crater point is also in the range where all chronology curves are merging. They are all in agreement, almost in agreement, or with each other. And the point is calibrating all of them very well, and even in the error ranges. So in my conclusion, that understanding the geology for measuring CSFD is very fundamental, that it's important to have a geologically homogeneous areas when you measure CSFDs. And now we have a lot more data. Consider that. Even though we have still some error bars, but the age, that absolute model ages from CSFDs and exposure ages are kind of in agreement. And this is the point where we could say that all chronology functions fit well. But still, I would want to have a further look in this. And of course, we want to adjust the area with new geological maps and slope maps. Then we want to use a newer fit for CSFD to we have to consider that if it's a good range of the crater population. And then again, we want to create more density maps or crater density maps to identify if there was influence of secondary craters. With that, I can stop now. Thank you.